Hi. Okay, so hi everyone. Thanks for joining this talk. Today I'm going to talk about what I think is the simplest way to build resilient applications. So I want to start this talk with this little snippet of code. Imagine this use case where you have a UI where a user can come in and put their credit card information and then say which subscriptions you want to subscribe to for, like those streaming services like Disney Plus, Netflix. And when the user clicks on the button, it runs this backend code. And what this backend code is doing is creating the recurring payment, and then after that, applying the subscriptions. And the question is, how can we make this code reliable? So I want to do a little thought experiment here and try to go over, how you would solve this problem today with the status quo of the tools that we have. So first of all, when the user clicks on the link, he runs this code immediately, but this is not good. You probably need some reliable retries, which means you probably need to put a persistent queue in front of it between your UI and the backend code to make sure you will remember that the user clicked on that link in the first place. But now you start having the problem that you have different retries for every new call, so you probably need to have some persistent request ID. Even worse, the user might click multiple times on the link, meaning it's going to create different events that will be logically the same, even though they are physically different. So sometimes you cannot even rely on the individual request ID. You need to generate some sort of idempotency key. And then you start performing some work, and for example, you interact with an external payment system like Stripe, which is going to give you back some ID that you also need to store and keep around, because in case something goes wrong there, you maybe want to cancel this payment reference that the Stripe gave you back. So you need to start storing some of these IDs, for example, in a key value store. And of course, every time you store something, you also need to think about how you clean this up. And for key value store, this is relatively simple, but it might be not so trivial when you deal with queues. And after that, every single operation that you do here will need some retry and recovery logic. And on top of all of this, because you have retries, you might incur in the problem of accidental concurrent retries. You might have, if you have this persistent queue, when it does the retry, it starts, for example, in a separate task, the execution of out subscription, you might end up having the problem that you have two concurrent retries of the same logical request. So in the general case, you might end up adding something like distributed locks or conditional writes to solve this. So, we started with a very simple function, and we ended up adding a lot of things, and that's how we end up doing, no? So it's the story of my life. So the point is, can we do something better here? So can we, let's say, reset and try to get this done better? So far we interacted, and in your if you build the backends, you know that you probably have dealt with any combination of these tools mixed together. So you use queues, distributed locks, key value stores, timers, and workflows. And the point is, can we introduce some abstractions that are closer to the business logic, that are closer to what you're trying to do rather than to the architecture of the system? And this is what the project that I want to introduce you today, Restate, is trying to do. It's trying to bring in these doable building blocks, as we call them, that give you several features that lets you model your application in a resilient way without having to deal with all these low-level concepts. So let's get into those. We have three macro categories, which we distinguish, and we start with compute first. This is durable execution. Now, durable execution at a glance is a very simple concept. The idea is that you have some code that executes some operations inside, and every single operation that is executed, it also gets persisted. So in case of a crash, anywhere in this code, or any sort of problem, network partitioning, whatever, the engine will detect that something went wrong, and it will try to re-execute the function, restarting from the point where it left, without re-executing what was already executed. And this gives you basically out of the box built-in retries, recovery of progress, and run to completion semantics. Let's look at this, how it works in practice. So you see here on the side is like the code that I saw before. I wrapped some of the instructions inside this context.run, which I'm going to show you in a second what it is. And on the other side, I have a restate, which is our durable execution engine of choice. And when we do a request to restate, and restate will act as a sort of a proxy between your code and like the external client. When restate receives a request, it will do the same thing that something like Kafka would do. So it will store it inside its own database. And then after that, it will try to execute the function. And when it tries to execute the function, every single thing that happens inside this function will get recorded inside restate. And restate for each individual invocation will persist what we call a journal, which is the log, essentially, of the execution progress. We generated a random UUID there. Then we try to execute and create the recurring payment, and this worked. Fine. Now we start looping inside the subscriptions. The first subscription goes fine. We subscribe to Netflix, but then when we try the next one, something goes wrong. Like anything can be. It can be there's a bug in the code. It can be, again, network partitioning. It doesn't matter. Something went wrong. So restate detects this, and what it's going to do is going to say, OK, this function didn't run to completion. I need to retry. And when it retries, it's going to execute this code again, sending it the partial progress. And this is what we see here. So it goes through the code, says, OK, context random, I already did it. Then it tries to apply the recurring payment, done. Tries to apply the first subscription, done. And then it goes on and adds the other subscriptions. And when everything completes, just returns back to the external client the result of the request. So I want to show you a little demo of how this actually behaves in practice. So I have here, let me make this bigger maybe, or can you see it, or shall I make it bigger? It's okay. Control Alt plus, no. Okay. All right. So this is the function that you just saw inside on the slide before. And I'm glossing a bit over the details because of the time that we have. But in Restate, you put functions inside something we call service, which is basically just a container of functions. And then you start you serve your functions to Restate just as very simple HTTP server. So nothing extraordinary there. And here on the other side, I have Restate that is already running here. This is a bit small, yes. But yeah, so let me show you now how you can invoke a function. You can invoke a function either using HTTP or just in this case, I'm going to show you how you can invoke a function using our playground. It's just a UI for experimentation. And you see here, this is the add subscriptions function. And I can go here. I'm going to now just copy paste this. All right. And I'm going to try to send a request. And the request went through successfully. So this one was easy, right? Now let's try to make this more complicated. There is a little bug in this code that I wrote that when I try to apply the Netflix subscription, the function will just fail. So let me now try to apply the Netflix subscription. And we see here that this is not returning anything. It's essentially stuck on waiting. And we can see on the other side here that there is an invocation that popped up saying that is in status retry, with Netflix being not supported. We can see here that in the code, we tried to execute the first time the function, and the function the first time executed successfully, creating the recurring payment, and then creating Disney+. But then afterward, it's stuck in trying to retry to apply Netflix. And we can see that this is just a scrolling, essentially, log of Restate trying to re-execute this function on and on and on until it can actually successfully complete the function to the end. So how do I fix this code now? It's because I made my life easier for this talk. the fix is going to be the simplest fix of my life, and just comment this line of code. And I'll now go back here, restart this, and compilation time. All right, we got it. Now give it a few seconds, and Restate will just retry to execute this. And let's see. All right, and eventually the function just succeeds. So we just restarted from the point where we left. We just tried to apply the Netflix subscription without re-executing the rest of the code, essentially. And we can also see here that the external client, which was in this case like my UI, just showed. I eventually just completed with the result that we were expecting to return. So this is, again, at a glance, what durable execution is. And it's like the fundamental building block that you would use to build resilient applications. But of course, this is not enough. This is just the business logic, right? In practice, when you build applications, you have several requirements. One of the requirements is that you need to interact with other applications that already exist out there, or third-party service providers. And this is where we provide some abstractions, which we call durable features. So the idea is that you can have a fault-tolerant communication across the services, processes, and time. We provide abstractions for functions to interact with each other in exactly one's fashion. We provide abstractions to model asynchronous interactions with third-party systems, which I'm going to show you in a second. And we also provide essentially an internal scheduler system that lets you both schedule asynchronous tasks, which will be executed, like, for example, in a year, or we can have just sleep that, again, lasts a year. And as you can imagine, a sleep that lasts a year is something that you don't want to lose track progress of. So in case your application crashes after 300 days, you don't want to restart from 1 year left. So that's where you can use the Restate durable features for. I want to show you now a little demo of another piece of code that is related to this. So here the use case is actually it's a very simple use case. We just need to do email verification. And the idea of this email verification flow is that, well, you send the user a link, and when the user clicks on the link, just makes the email verification go through fine. And on top of this, we also want to have an upper bound on the email verification process. Let's say you want to have the email verification to last just like the link to be valid just for 1 day, for example. And then on top of this, we add another requirement that is that let's say every half an hour, you want to send the user a reminder saying, hey, please click on the link. And every time you send an email, you want to make sure that the email you send is always the same. So how do we solve this with Restate? So we have this functionality that we call the Wakeable, that is basically like a Tokyo one-shot channel, for who of you that knows Tokyo, which gives you a receiving side, and then it gives you an ID, which you can use to complete the receiving side. And then what we do is that we use this Wakeable essentially as the secret to send on the email. So when we send the email will contain encoded essentially in the URL, it will contain this ID, and then when the user clicks on the ID, it will resolve this Wakeable. And then what we do is that we just create a timer using context.sleep, which is our version of timers that is durable, gets persisted, and it can be as long as you want, and it will make sure it will get persisted. And then we do the usual pin dance, which is something we just need to do. And then we enter in a loop. When we enter in the loop, we create this reminder timer, which is going to be, in this case, I think 30 minutes long. And then we just do a select. So we wait for any of these events to come first. Either the user clicked on the link, or the reminder timer fired, meaning we need to send a reminder email, or the verification timer fired, meaning we need to return a business logic error saying the email verification expired. And for completeness, when the user clicks on the link, it will call this function click, which simply resolves that signal that we saw before. So the interesting part of this code is really like the properties that it has. So if you crash, for example, when you are waiting for the verification timer, you will restart without restarting that timer from the very beginning. Or another property that is very interesting is that here we are doing this select is waiting on the 3 asynchronous events that might come at the same time. But thanks to restate, the interesting part is that you will handle only one event at the same time, so you won't have any concurrency issue when trying to handle these events that might come from different sources. So if you think about this, how would you build this without restate? So you probably need at least a key value store where you can store the ID of the verification or the secret of the verification. Then you probably need some external scheduler system where you can schedule this timer that are very long, because of course you cannot have a 24-hour timer inside the process, because if the process crashes, it starts from the beginning. And and then you will need some way, because you have different event sources. As one event source is when the user clicks on the link, but the other event source is the scheduler. You need to handle the concurrency issues of having these 2 events that might come at the same time. While with the programming model of durable execution, this is just as simple as writing it in the same way you thought about this. Create some timers and then either wait for the first event to come. So that's, I don't think we have time for running this, yeah. Or maybe we do, yeah. So let me try to run this. All right. So I'm gonna run Karkaron part 3. All right, and then I need to do one little operation, essentially telling the engine to register this new service. And then now let me try to call it. All right. So I'm going to send this request here. This is the request here is waiting for the response for verifying the email. And then we see in the log here that we got this logged. So we got a sending email to Slinky developer with this, essentially this is the ID to simulate the click. And actually when I do something here, I just want to kill this process. Yeah, which is supposed to get killed. That's what happens when you use main. There we go. And we can see here that this is the restate log that actually tried to, at some point, it just lost the connection. It tried to reconnect a bunch of times because it figured that it lost the connection with the original service. And now let's just try to complete this awakeable. So, here we got a timeout request. Oh yes, because I didn't add the timeout. Yes. Let me try to rewind this. I'm improvising here, so. All right, so, all right. Now it goes here. Okay, we got this ID here. And now let me try to complete this. And we see that on the other side here, we got email verified. So when we clicked on the link, we got the email verified. If now I try, just for the sake of trying, to lower down this timer here to, I don't know, like 5 seconds, and run this again. Okay, it's running. We see that this request after 5 seconds will just stop working and say that the verification expired. So this is a bit of like how you can use this concept of durable futures to essentially model applications that have different concurrent events and have reasonably complex flows of orchestration mixed together. So there is one last bit which we provide that is important to build your backend applications, and this is of course the state or better business data. And for that, we provide a functionality called virtual objects. So the idea here is that if you think about the example I showed at the beginning, we have these add subscriptions. That is a functionality of a user service. But let's say that now I want to store, after I add the subscriptions, I want to store somewhere the subscriptions they added for that user. And the point is, what if we need now to model this as a sort of a stateful entity? So what if the user becomes basically an entity? And this is the idea of this of the API that we call virtual objects, where basically each individual service can have an identity that is, in this case of the user, can be just a user ID. And this identity is then used to address a key value store isolated that is per essentially per entity. So we can see here a bit how it works. We have this user service that is add and remove, and we can have like 3 different users with different IDs, and each one of them will have its own key value state associated with it. In this case, like user 1 as Prime, user 2 as Disney, and so on and so forth. And because the state changes participate in the doable execution, the cool part about all of this is that you will have state of the business data consistent with the state of the execution. And not just that, what you also get is that because, of course, like now we have 2 handlers that they need to concurrently read and write state. So now we got into concurrency issues, and to solve that, restate gives you a queue per key semantic success on the virtual object. So for example, here we call add of user 1, and then we also call add remove of user 1, and the way restate will behave is that it will give you just a queue essentially on the user 1, which is as opposed to, for example, Kafka, for who of you that uses it, that gives you essentially concurrency per partition. In case of restate, you get concurrency per key, which is a pretty useful thing. And the most important part of all of this is that essentially all the code that you actually run is stateless. So you can run your code on Lambda, you can run your code on any serverless platform, and this is just going to work fine because the state is inside restate. And this, like the virtual objects especially, they have several use cases around things like digital twins or agents in the AI world, durable actors, state machines. It's also pretty useful for stateful event processing. You can imagine how the state just contains the state of the event processing. Yeah, I don't think we have time for demo. But yeah, like maybe I'll just go to the closing remarks here. So we started with these concepts as a starting point, and then we said, okay, can we bring in some concepts that are just closer to the business logic? And this is what we did here. We provide you features that are, or better, we provide you concepts that are much easier to grasp and much closer to the business logic than queues, distributed logs, key value stores, and so on and so forth. And this is what our project is aiming to do. If you want to try it, it's just a single binary written in Rust. It's basically dependency-free because it contains a little database inside it. I'm going to tell you in a second about this. You can just download it. It's free to use. And you can build applications using Rust, but you can also use the TypeScript, Java, Kotlin, Python, Go. And the beauty of this is that because all these applications behind the hood will use the same protocol and the same log system, they will also have a consistent interaction between each other. So you can write a Rust function that interacts with a TypeScript function in exactly one's fashion. The way it works under the hood, and actually we have a few blog posts that describe the details and the inner details of the system, is that it's essentially a self-contained system that contains inside it essentially a log that is very much like Kafka, and uses RocksDB for writing stuff to disk, effectively. It has a control plane on top that is just uses just as its own metadata store, I think based on Omnipaxos, if I'm not wrong. And on the 2 sides of the log, on one side you have, well, the ingress, which is where I showed you a sent HTTP request to. And then on the other side there is essentially a replicated state machine that does the hard job of figuring out at which state, which point of the function you are, if you need to retry, if you don't need to retry, and all these different details. It's handled by this replicated state machine. And when you do request, and also this state machine is the one that actually pushes invocations to the application code, which can be, again, deployed on Lambda. We have, as an example, Cloudflare Workers too, and just on Kubernetes is also fine. We got many examples, and many people that are using this for various reasons. Generally, it's projects like Restate make sense in environments where you need data to remain consistent, you need high availability, and things like this. One example is that we have this user that is basically using Restate to synchronize different legacy systems that are all based on queues and webhooks. So it sends a message to the legacy system and then just creates an awakeable that waits that it gets completed or when this legacy system replies back, calling another handler. And we have another use case of this company that is using Restate to essentially orchestrate physical machines in manufacturing plants. And it models all these physical machines as digital twins inside Restate, and it keeps synchronized essentially with events, the stuff that comes out of the physical machines and gets inside Restate. And then it uses Restate to essentially coordinate the various actuations. We got, of course, some examples with AI because it's 2025, and you got to have that. And yeah, and that's pretty much it. So thank you for joining this talk again.